Welcome to my UOP-CS2204 class. We're talking Unit 6, the Transport Layer, specifically the User Datagram Protocol, known as UDP. We have a few topics we're discussing in this lecture: stop-and-wait transport, sliding windows, UDP, QUIC, TFTP, overall transport issue, and we're going to end it with RPC. Learning outcomes. We'll be looking at stop-and-wait file transfers and issues that may arise with that. We're going to look at the RPC protocol. We're going to look at UDP and kind of see how that relates. We're going to end it with a quick conversation about QUIC and some of the advantages QUIC has over TCP. Overall breakdown, there are 10 sections in this lecture. We're going to start with the OSI model, talk about protocols, talk about building reliable transport communication, slide into our Windows sliding methodology. We're going to talk about bottlenecks, QUIC, move from QUIC into Simple Talk. We're going to end that part of the conversation with a utility called Netcat, and then we're going to end the overall lesson with reviewing two key protocols that use UDP. And that will be the TFTP and RPC protocols. So let's go ahead and jump right on in. So let's go ahead and talk about the transport layer. We're talking the OSI model here. So we're dealing with layer 4. The role of this layer is it is used to establish a temporary communication session. It provides the connection-oriented data stream support. This includes things such as reliability, flow control, and multiplexing. So what does this actually mean? The important takeaway from the transport layer functionality is that it provides that temporary communication session. So you have a source and destination. They will actually build a communication session between one another for them to share data. Once that data has been shared, there will be a termination of that session. So if I have multiple sessions being shared with a destination, as each session comes to its natural conclusion, they will close. Meaning, if someone is able to capture packets from one of those sessions and try to reinitiate a connection after the session has been terminated, it won't matter. The termination has already occurred, so source and destination will no longer have that session open. So that's one of the forms of security and reliability that is built into the transport layer. So how do we actually discuss those sessions? Well, the nice thing is this deals with end-to-end communication between hosts, source and destination hosts, and it's done through a port number. And a port number is a 16-bit address used to identify any client-server program uniquely. The source will have a random port, while the destination may have a specific port. For example, a website uses port 80 or port 443. Well, you can have multiple clients connecting to port 80. Well, the server will distinguish each session based off of the random port number that each sender is actually using. That's how the web server knows how to send data back to the individual sessions, because of that randomized port number on the sender, on the source. The main responsibilities for the transport layer is, again, tracking individual conversations, and the nice thing with this is segmenting of data and reassembling of data. Segmenting is basically just a clever way of saying chunking up large packets so that it is more manageable. So before we talk about the segmenting portion a little more in depth, we have to talk about data integrity. So assuming that a source is sending something to a destination and the destination is responding, there has to be a few things there to control that communication. One, flow control. This is going to be a mechanism that is used to ensure that data is flowing at an appropriate rate. Not too fast, not too slow, and things of that nature. That way, the destination and source can send a good amount of data at an appropriate speed that they both agree to. Sliding window is part of the flow control, which we're going to talk about coming up in a few slides. But part of that flow control is about making sure that we're sending good data. So that means no errors. Layer 4 deals with corruption by implementing type of error detection codes. They also do checksums, and they verify that each packet actually is sent and it is not molested. The data integrity is intact. And they actually will acknowledge or negatively acknowledge NAC and ACK to ensure that these packets have been received and are in good standing. The data integrity has been verified. That way, if the data integrity is not there, a negative acknowledgement, a NAC, can be sent and the packet can be resent or corrected. TCP and UDP both are the two main protocols in the transport layer. Both have functionality in multiplexing. And part of that multiplexing is that segmentation. Again, segmentation is chunking of a packet. And part of that would be labeling the data chunks according to the conversation. Is there a sequence number that we have to attach them to, or do we have to do a data number? That way, we can ensure that the data can be reassembled in a specific order, assuming that is what we're wanting. There are two main protocols for TCP, or for our transport layer. That's TCP and UDP, which I've already said. TCP focuses on reliability. UDP focuses on deliverability. There's a lot of overhead with TCP, so that's one of the concerns. UDP is best suited for real-time traffic, or some type of traffic that has a time component, because with the lower overhead, UDP is able to send faster, but it's not as reliable. So you give up reliability for time. So how does UDP allow for data reassembly if we're not dealing with some type of reliable transport? Well, UDP actually allows for timestamps so that we can see which packet was sent before which other packet. That way reassembly can be based off of timestamps instead of a sequence number. So we already talked about the conversations. We already talked about source and destination port numbers and how they allow for individual communication. You have to remember that with a service, the destination port number is going to be typically a fixed port number. We have services that will reside on those port numbers, and the sources, the clients, can be any randomized port number, and that's how we uniquely identify those communication. With that, we have to understand that port numbers like TCP port 80 is different than UDP port 80. While some protocols can operate on both protocols, meaning we have some services that will use both TCP and UDP port 80. We have some protocols that will use one protocol, TCP or UDP, and the randomized port number. So it just kind of depends on the task that we're trying to accomplish. Both TCP and UDP have their own unique header values. These values allow for the manageability of those simultaneous communications. A header is what actually precedes the data packets. The header will actually have all of the detailed information used to accomplish that layer's functionality. Layer 4, transport layer, is dealing with ports and simultaneous end-to-end communication. So our header is going to be more focused on our port numbers. And again, the port numbers from the source should be unique. The destination will be a pretty standard set because whatever resource that we're going to be requesting typically will be found on known ports. Port numbers again will be come in pairs, source and destination. Source will be dynamic, destination will be based off of the server requirements. So let's go ahead and let's look at the different protocols a little more in depth. TCP supports packet delivery confirmation via acknowledgements. It's connection oriented. Connection oriented means it requires a session. It actually will establish communication and it will use that establishment to send and receive data. When conversation is done, it will tear it down. TCP has three major functionality. It has numbering that will track data segments. It has acknowledgements for each data segment, and it has a retransmit any unacknowledged segment after a certain amount of time. Basically, what this allows us to do is, if we're sending a data packet and it doesn't arrive, if we don't see a response or an acknowledgement that it has arrived, we can resend it. That's overhead that is going to be there. UDP doesn't do that. UDP provides the basic functionality for delivering packet segments between the end-to-end communicating hosts. Very little overhead. While it does do data checking for data integrity, it doesn't make sure that every packet is delivered. This is known as connectionless. It doesn't require a formalized session connection between sender and receiver. The sender simply starts sending data packets. Data packets are often called datagrams also. So what ends up happening is we just start sending data and we hope it gets delivered. This is going to be part of the non-reliability portion of our UDP protocol. If we're sending data and we don't know if it gets delivered, what happens if it doesn't? Well, nothing. It just doesn't actually get processed. That's all. If you're watching like a video in real time, if it had to stop and wait for every single packet to be received in order before being displayed, it would constantly be buffered. So we don't like that. That would not allow us for real-time communication. Where with UDP, we don't have to do that. If we're watching a video via UDP-based protocols, if we don't receive every single packet, it just doesn't display that frame that that packet had. So the video may be a little choppy, or we may not even notice it. It just kind of depends. Keep in mind, if we're looking at a video that processes 60 frames per second, 60 FPS, well, if we lose one frame, so we're now looking at 59 frames per second, are we going to notice that one frame? Maybe it's 3 frames. It would not matter at that point. The number of frames would be pretty significantly low for us to actually see it. So that's why UDP is a little bit better. It just drops the packets that we don't receive. TCP is going to be predominantly for anything that requires or ensures or needs the assurance that data has been delivered. UDP is great for anything dealing with live content, audio, video, things of that nature. So let's go ahead and let's look at UDP, since the focus of this lesson was supposed to be on UDP. Well, UDP, again, simple and fast. Here's the header. We have a source and destination, each both 16 bits. We have a length and a checksum, and after that, everything is just data. So we have a total of 8 bytes for our overall header. Each one of these fields, source, destination, length, and checksum, are all 16 bits. So 16 plus 16, so we're looking at a total of 64 bits out of our overall datagram. UDP, that means we'll add 8 bits of overhead to our data. A typical data packet should be about 1500 bytes. So 8 bytes are going to be just the header portion. Now keep in mind, we're also dealing with our header here, our layer 3, still has to encapsulate our packet, and then our packet still has to be encapsulated into a data frame as well. So it's not just all of the data can be in this section. Each layer is going to add their additional overhead. So we'd have to accommodate for that as well. So again, the main argument here is UDP has lower overhead, but that means we have to weigh it on our reliability. UDP is connectionless oriented, so no sequence numbers. That means UDP will simply reassemble data in whatever order it received it. The application must identify the proper sequence if that's necessary. That's going to be where the timestamps come into play. We've already discussed the UDP server process, looking at source and destination ports. So the question really is, how can we build a reliable transport based off of UDP if UDP is not made for reliability? Well, the nice thing is, within reliability communication, within just general communication, reliability is not necessarily always a concern. When we're looking at, are we sending data via TCP or UDP, there is an assumption that the data network that we're sending over is going to be 1, secure, and 2, sustainable, meaning it's going to be functionable. So when we're building a reliable transport network, we have to look at a few core concepts. One of the big ones is this transmit on timeout, ROT. Well, within ROT, whether we're talking TCP or UDP, ROT will require a sequence number. This is part of the sending of data. Again, this is not going to be so much of a sequence number like the formalized TCP will use. This is more of a general, are we sending the appropriate amount of data? So ROT will use a sequence number to send data. UDP can actually use this functionality for sending data using UDP over this. So stop and wait SAW is a version of ROTs, and how stop and wait functions is the sender will send only one outstanding packet at a time. If there's no response, the packet may be retransmitted, but the sender will not send a datagram until it's received an acknowledgement. Again, this is not formalized session creation like TCP would use. This is more just verification that packets were received. Basically, each side has only one packet in the play at a time. I send you data, you send me an acknowledgement. I send you data, you send me a second acknowledgement. I send you data, you send me a third acknowledgement, and so forth. Well, again, this entire process is not very reliable. It's not very effective or efficient. This is part of the way that TCP functions, but UDP has certain protocols that can take advantage of this. But again, it's not very efficient because if we're sending one data packet and then having to wait for an acknowledgement for every single data packet, that then increases the overhead of that packet. That real-time component is slowly going away if we're having to do this data acknowledgement transformation. So what we end up doing is we have what's known as a sliding window. Sliding window is we can send X amount of packets, That's typically known as a win size or a window size. If I send 5 packets, let's assume that's what we're agreeing on, then the destination can send 1 acknowledgement saying they received those 5 packets. The basic idea of a sliding window is we can send as many packets as we agree on, and then we will receive an acknowledgement based off of that packet count. So if we send 5, I get 1 packet count per 5 packets. However, if one of the 5 packets don't arrive, well, you don't get an acknowledgement for that. So all 5 packets have to be retransmitted. That's an issue. In UDP can actually use sliding window, but in UDP, the window size is a fixed length. Once source and destination agree on the window size, it cannot be changed. TCP, on the other hand, has a variable sliding window size. So there is some give and take with this. And again, when we talk sliding window, UDP can definitely take part of this functionality and use it. We're not doing a formalized session creation, so there are no sequence numbers here. We will actually just label the data with a label tag, and that way we can ensure that data has been sent. And this is more about verifying that data was sent and not corrupted. Not so much did you receive it, but we're talking more error detection. We're talking sliding window and UDP. 6.5 is about bottlenecks. A bottleneck is typically when we're looking at like packet delay or bandwidth or real-time transport, product sequencing. This is about the amount of data that can be sent before a response is received. Going back to that sliding window, can I send 10 packets? Can I send 8 packets? When am I expecting my first response saying that you received my data sent? Because again, UDP does not formally set up a session. So figuring out how much to send before our first response is part of that structure of UDP. Part of the bottleneck functionality will play a huge role in the analysis of the transport layer protocol. Bottleneck is where we actually have one resource, exit interface, input interface, one object that actually is causing a delay in the sending of data. So this is typically the slowest link is going to be known as the bottleneck link. It doesn't always have to be a link, it could be a device. Maybe we have a outbound router that is struggling to process all of the packets per second that are trying to be sent. So the bottleneck there may be that device, or more specifically, what part of that device is not allowing for that communication. In that example, it may be a processor that's overloaded on that router that's not allowing the packets to be processed as they leave. That device would be the bottleneck. The literature points out one very important thing, and that is bandwidth times delay. And this is one that we're going to be discussing quite a bit for our transport layers, both UDP and TCP. The text will actually abbreviate it capital B, capital D, capital P. Bandwidth, delay, product. So that is our overall bottleneck. Moving on, we have what's known as QUIC. QUIC UDP Internet Connection. This was created by Google, and essentially what QUIC does is it takes advantage of the UDP's freedom from the head of the line blocking. One of the downsides to QUIC is it's a non-standard programming interface, but Google being Google fixed this by actually just allowing QUIC to be distributed through all Chrome web browsers. So Google actually has their own specific communication protocols that take advantage of the transport layer. Alright, so let's talk about what QUIC is a little bit more in depth. So QUIC can be in fact viewed as a transport layer protocol specifically tailored to things like HTTP and HTTPS. While understanding that it's more similar to UDP because it's based off of UDP, security is one of those major concerns. But I'm going to hold off on that part because we're still talking about advantages of QUIC. One of the nice parts of QUIC is that it supports multiplex streams in a single connection. Basically, there's multiple components of a web page that can be sent via a single UDP connection. Part of that means a lost packet will block its own stream until it is retransmitted, but the other streams can continue without waiting. In earlier versions of QUIC, this was not really supported. So basic error detection was an issue with QUIC. In most cases, QUIC will eliminate the initial RTT needed for setting up a TCP connection. Again, QUIC is based off of UDP, so that session buildup is not normally necessary. This will allow data delivery with the very first packet, meaning data is able to be sent faster. However, as otherwise accepted data in the first packet opens the recipient up to certain spoofing-based attacks. So that's where we have to start talking about the downside. QUIC is definitely more susceptible to spoofing. Security is one of the largest issues with QUIC. So while authentication and encryption provides more secure methods of transporting of data, they're also responsible for one of QUIC's major drawbacks. Since the packet header contains less plain text information than those with TCP connections, troubleshooting is also a huge drawback. Things like traffic regulations or network management has become more difficult because of these QUIC connections. So 3 main areas where QUIC is a drawback: security, troubleshooting, and network management. Those are the 3 main drawbacks of QUIC. One of the other fun parts is QUIC needs to be enabled on web browsers. While it comes with Chrome, you have to turn it on. It also works in Mac web browser as well, Opera. All of this, they're classified as experimental protocols where you can turn on QUIC, but there's drawbacks. That security aspect is a huge drawback. So, moving away from QUIC, let's talk about SimpleTalk. SimpleTalk is also based on UDP. This is one of the earlier standards of our socket programming. That's what SimpleTalk is. Assuming that there are lines sent with each end-of-line marker, meaning as we're sending communication, we will actually tag each communication with a end-of-line marker. This allows the router, when they are querying or queuing mass amounts of packets, to see where the end of each packet really is. That's part of that end-of-line marker. Again, server-side IP and port numbers combined will make a socket address. A socket address is both IP and port number, so that's one of the important things. Every operating system will use a different end-of-life code marker when they're transmitting data. However, when we get to the TCP version, we'll be talking about end-of-line markers in a slightly different way. Overall, SimpleTalk was used to use the socket address for fast delivery, typically in a one-way nature flow. Instant messaging, for example. It will send data, and that will be it. Once it gets delivered, the destination can then respond with their own instant message, and back and forth. That's what SimpleText was created for. SimpleText has both server and client-side setup. The server side, it will be having a designated port. it must create a socket for receiving communication. It will bind the socket to the IP address. It will then look at receiving packets sent to that socket. For each packet received, it will print its sender and its content. That's for the server side. For the client side, clients will have to look up the server's IP using DNS. That's basic functionality. It will create an anonymous socket. We don't really care about these because that will be the randomized port number from our source. If you do a ARP lookup in a computer, you will see anonymous connections. That is the connection between your device and a web-based resource typically. That is because, again, we're randomizing the source port going to the destination. It will read a line from the terminal and it will send it to the socket address. Normally, reading a line from the terminal, that's if we're doing it via a CLI. If we're doing this from a web browser or a web application, those will be reading the communication and then sending it to the appropriate socket address. And again, that will be the server IP and the server port number. That takes care of our simple talk. We have a utility that we can actually check for communication. Netcat, also known as NC. NC is used for sending individual UDP or TCP packets. We want to test to see if a socket is actually receiving information. We can send an individual TCP or UDP packet to that address. And again, we can send a single packet or we can send multiple packets. The nice thing here is Netcat is available in all major operating systems. There are two main switches when we're talking Netcats: TAC-U and TAC-L. TAC-U is used when we are requesting a UDP port. TAC-L will basically tell Netcat to listen instead of sending. So if you want to see if you're able to receive something on a specific port, you can do NC, TAC-L, and then port number. If you're expecting a UDP response, it would be NC, TAC-L, TAC-U, and the port number. That is Netcat in a nutshell. Netcat is actually a very powerful tool when we're doing basic network reconnaissance. So I'm going to leave Netcat alone for later lectures because Netcat is way more powerful than just this. This is a good troubleshooting tool, but it's used for more than just troubleshooting. So as we're getting close to wrapping up, we have two main protocols that use UDP that we have to talk about. Trivial File Transfer Protocol, TFTP, is one of them. Basically, this is going to be one of the first or earliest versions of a real-time protocol based on UDP, known as TFTP. It is very similar to FTP, except TFTP doesn't set up sessions. It sends data, and that's it. TFTP uses port 69, and it actually will do data block numbering to verify the integrity of the data sent. Part of that means that the data blocks will begin numbering at number 1. It will send a data block, and it will expect an acknowledgement. And it will keep doing this until all the data is transmitted. With TFTP, there are 5 main packet types. The packet types are a read request. Basically, this will contain the file name and a text binary. A write request. This will be the write request. There will be a data, and this will contain a 16-bit block number and up to 512 bytes of data. The next packet type will be an acknowledgement. This will contain a 16-bit block number. And lastly, there will be an error packet type, and this is for certain designated errors. Basically, all errors other than unknown transfer ID are caused for sender termination. Data blocks will have to be acknowledged per block. With TFTP, data will be up to 512 bytes of data. Meaning, if we're trying to send a 2,000 byte packet, or a thing of data, well, we're going to break them up into 512 chunks of data. So that means 4 packets will have to be sent using TFTP to accommodate a 2,000 limit. If we're sending a larger one, basically you take the number 4,000, divide it by 512, or 8,000, divide that by 512. So the data size divided by the max data length will give us how many packets we need to send. So we're taking a large chunk of data and we're breaking it up. That's called fragmentation. Our last major protocol is this remote procedure call, RPC. Basically, the concept behind RPC is that one host will invoke a procedure on another host. They will send a parameter and return values that are transmitted back and forth via UDP. The point of UDP is that on a local network, we can fall back on a rather simple mechanisms for timeouts and retransmissions. Basically, the term request reply takes a hold here. UDP is well suited for request reply, not just within RPC, but in other options. Again, we will send a request, we should get a reply, and then we'll send an acknowledgement. Keep in mind that there are issues with RPC. This is very simple and this is nice, but there are concerns. The 3 main disadvantages of RPC is it's not a standard. It's not really flexible for the hardware architect. It's only more interactional based. And lastly, or third, there's an increased cost because of the RPC. That functionality is not standardized, so that's one of the concerns. While some of the advantages is the RPC does support process-oriented and thread-oriented models. Internal messaging pass-through. Basically, this is hidden from end users, so end users don't have to see this. The simplicity of the request and reply model, and many of the protocol layers are omitted by using RPC, thus actually allowing for better performance. So this actually concludes this week's lecture. If you have any questions, please reach out. Thank you.